Hello everyone, welcome to this video. My name is Amir Ahri. I'm a Google Earth Engine expert. Today I'm going to show you how we can get temperature data for each land cover class using available land cover products in the Google Earth Engine platform. So go to the Google Earth Engine platform, and now in the first step we need to identify region of the interest. You can use this tutorial for all around the world and no matter where the ROI or region of interest is. For example, same as other tutorials, I'm gonna select a part of my own country. So northwest of Iran is my study area, and also I select this region as a location of interest. And you can use drawing rectangles, drawing tools and rectangle tool available here for all around the world, and also any places or any locations that you want to study. So then through the map.center object, we need to have a focus on the study area that is renamed as geometry and available here. Then we need a unique land cover map for the region of the interest and variety of products and data available in this regard. For example, one of the most important land cover products available in the remote sensing community is a modest land cover product with 500 meter spatial resolution and annual temporal frequency available since 2001. So through the search places and dataset, just write modest land cover, just like that. Modest land cover. As you can see here, modest land cover annual with 500 meter spatial resolution is available here. Make a new variable. This is LST, meaning land cover equals to image collection. We are assigning image collection to land cover variable. Next, we need to make a unique land cover class, or single land cover class for this region. As this is as image collection and the land cover maps available annually, we have 21 land cover maps for this region. Let's see. Print land cover. In the right panel, you can see that 22 elements or 22 land cover maps available since 2001 to 2020. And now we want to make a single land cover map that's showing the general classes for this region. And one of the important methods or statistical methods helping us to find the most frequent classes is .mode. .mode help us to find the frequent classes in this region to make a general maps, and then we can, based on select different land covers and get temperature data for. So .mode, and as you can see, print LC. Now you will see that now only one land cover is available for each pixel the frequent class estimated or calculated. And then as you can see, different land cover standards are available in this image, but mostly people, or typically in remote sensing, we use LC type standard number 1, LC type 1. This is a target band we need to work on. So, and for the next step, we need to visualize the land cover map created for this region. To do this, go to the land cover data description. In the descriptions, open it in a new tab. Here you can see that there is a code example here helping us for the visualization process. And as you can see here, a variable as IGBP Landcover Visualization characteristic, including minimum, maximum, and palette color already available here, and we don't need to write this code again in our program. So, and now copy this part of code and back to your code again, paste it here, and now through the map.add layer we can do visualization based on this characteristic. So map.add layer, we want to visualize Landcover maps based on the IGBP Landcover visualization, or simpler is visualization parameters. And also next, the name of the layer could be, for example, map for the study area, and in order to avoid automatic loading or automatic visualization, I'm using false at the end, and false helping me to show the result whenever I want. So then run the code. Code is running, and after a few seconds you can see the created map through the layers option available here. You can see that this map is globally available, and you can pick everywhere you want, or you can select everywhere you want for the further estimations. For example, I can change my study area from the northwest of Iran to the north of Iran. For example, in the north of Iran, we have forest area, croplands, water, and also urban area, and we can compare their temperature compared to each other. So, and next, in order to have focus on our study area, we can, for example, clip the map based on the geometry that is drawn by the rectangle. Now you can see only the Landcover map that is available for our study area. So by the inspector, if you click on each pixel, you can see a value that's related to one class. For example, class number 12, back to data description and bands, there is a Landcover Table class that helping you to interpret the values regarding to the land covers available in this region. For example, number 12 showing croplands, meaning at least 60% of area is cultivated or cropland. So, and another pixel, for example here, number 17, and number 17 showing water bodies. At least 60% of area is covered by the permanent water bodies, not seasonal or not temporary water bodies. So, and now I want to, for example, get the temperature of the water body, and just I want to have the temperature of the water bodies in this region, not the temperature of the rangeland, cropland, forest, and so on. So to do this, we need to first select the water class here, and then calculate the temperature, the average of temperature only for this region. To do this, it's very simple. To do this, make a new variable as, for example, water threshold equals to, we need to make a shapefile from the water pixels. So here from Landcover, please select through .equal those of pixels including number 17, and then we need to show what happened. Map.add layer, water threshold showing a binary image by 1 and 0, in which number 1 showing water and number 0 showing non-water pixels. Water threshold, leave visualization empty, and the layer name is water threshold, and then false. Again, here you can see water threshold. Finally, we have a map that's showing only water bodies. And in order to have focus on our study area, clip it based on the geometry. And now you can see the binary image showing water areas by value number 1. So in the next step, I want to remove the dark region that's showing value 0. So to do this, we need to use update mask. Make a new variable. Now we want to mask the 0 values from binary image. Water mask equals to get water threshold, update mask, again water threshold. This code helping us to remove 0 values from the image. If you followed my previous video in the YouTube page, you can see that how much update mask, clip, and also the other functions I'm using are applicable in the Google Earth Engine platform. You can do most part of your projects without coding techniques out of Earth Engine built-in functions. Just you can use built-in functions to do routines and also to extract valuable informations. And also remember that when you are using available functions in the Earth Engine, you can have access to provide a faster code, and also with simpler structure, and also you can use more, you will have more efficiency in this platform. But for example, imagine that instead of .map function or something like that, if you use .for or something like that, the speed of processing decreased a lot. So, and now through the map.add layer, I want to show what happened in the water mask again. So now we want to have water mask and then false. Water mask, as you can see, only water is available here, and without any value 0 or dark region. And then clip it based on the region. Run the code again, and finally you can see the water mask. This is the original map, and you can see only we select the water area. And now I want to convert water mask from grid structure to the vector structure. I want to convert it to a vector, and because I want to use this vector for the study area. So it's very simple. Make a new variable as water vector layer. Water vector layer equals to get water mask dot reduce to vectors. Reduce to vectors, helping us to convert this layer, a grid layer, to a vector layer. So no need to use reducer. The only thing that is important here is geometry, that is equals to the geometry origin of the interest, and the next is the scale. And the scale is very important because it's showing the accuracy of the borders. For example, if you use a scale, if you set 500 meter, same as a spatial resolution for a scale, you will have a vector layer consistent with the spatial resolution. But if you use coarser values, such as 1000 or 2000, you will have a generalized vector layer. I will show you how it works. And finally, use that union with margins as number 1 to reduce to remove the to avoid from a multiple recording in the vector layer. For example, without union, when I print water vector, you will see that in the panel, in the right panel, you can see that we have 12 elements, 12 sections. And if you want to merge all these 12 elements into one element, because all of them showing the water body, that union with margin number 1 is helpful. For example, now I will have one vector layer with one section and one element without multiple elements. That is very useful for the further programming. So, and now I want to show you the vector layer that is created for the water. Through the map.add layer, use water vector here, yes, and then leave the visualization empty, and here we have water vector. Write the code again, and water vector is available. Now we have a vector layer for this region, and now we can use it for the and also we can use it as a target area for the temperature estimation. How we can get temperature data only for the selected region? That's very important thing that I want to show you in this tutorial. So now for the first step in this part, we need to call MODIS temperature data. Through the search places and dataset, write MODIS temperature. MODIS temperature, you can see that diverse set of products available. For example, one of them is Terra land surface temperature with 8 days temporal frequency. I'm one of the biggest fan of multi-temporal data. For example, I prefer to use 8 days data compared to the daily one, because 8 days data provided higher quality images with less noises and cloud cover. So import it into the code, and here we have image collection number 2. Make a new variable, for example, temperature equals to image collection number 2. And then we need to set system timers. We need to set a start date and a start time through the filter date. So filter date, time start here, for example, is 2001 and time end is 2024. As there are different bands in the MODIS temperature data, if you go to the bands, they are available. Only we want to use land surface temperature with 1 kilometer spatial resolution, that is for day. And also you can use day and night data together. It depends on your target or purpose regarding to the project you are working. So for example, I want to use LST day 1 kilometer with a scale factor 0.02. So here, as you can see, throw.select, select target band, LC type with 1 kilometer, and then we need to apply a scale factor on each available data in this variable. So that's map helping us to make a function as an img and then write the program. That's map. So make a new variable. For example, the new variable is bands, or without any variable you can write this part of code. Just return each img dot multiply to 0.02 with the properties of input images. Having properties of input images, specifically system time start and system time end, is necessary for the further time series analysis in the Google Earth engine. That should be considered in your work. So, and now throw the print, make a chart image series that's showing you the temperature variation for the water vector. User interface dot chart dot image dot series. Couple of arguments available here. Replace image collection by temperature because we want to show the temperature. Instead of the region, you need to set the vector layer that is created, which is relevant to the water, and here a water vector comes here, and then if you want to get the average value of water for each day, the average value of water area for each day, use Earth engine.reducer.mean. And a scale should be considered here as same as spatial resolution. For example, the spatial resolution here is 500 meter and a scale is 500 meter. The X property, as I mentioned earlier in the previous tutorial, should be equals to the system time start, because the system time start is the only properties including the acquisition date for each image and helping us for the time series analysis in the Google Earth Engine platform. So run the code, and after a few moments in the right panel you can see the chart is generating. After chart is generated, you will see the temperature of the land surface temperature for water area in this region. That you can see it is based on the Kelvin unit and ranging from 280 to 300 Kelvin. If you want to convert it from Kelvin to Celsius, there is a simple equation. Just subtract the Kelvin values from the 273.15. After this, a new chart created that's showing land surface temperature based on, for example here, yes, degrees Celsius. Now the temperature varies from 10 to 30 degrees Celsius. So imagine that now we want to get the, for example, the temperature changes for the urban area in this region. So if you load the primary map here, you can see that the urban areas showing with gray colors. And now if you change the transparency, you can see that these regions, the gray regions, equals to the urban area. So now by the inspector we can find their value. The value of this region in the classified map is 13. If you go to the data description, to the bands, here there is a table that's showing number 13 including urban and built-up areas, at least 30% of impervious surface area. So now we can repeat this process for the urban structure. But this time I want to make a function that's helping us to do this process on the classified image and calculate the temperature for urban area. So make a function for urban layer. Function, the name of function is urban layer, and each input image consider it as an IMG here. That is a single image actually. That image would be the Landcover map. And now make a new variable in the body regarding to the urban threshold. From input image, I want to select class number 13 or pixels showing or including class number 13. So next, another variable for the for masking 0 values. Urban mask equals to get urban threshold dot update mask urban threshold. So after getting after producing urban mask, and now we need to convert the urban structure, urban class from grid structure to the vector layer. So now make urban vector equals to urban mask dot reduce to vector. Reduce to vectors, helping us to do this conversion without any complexity. So, and the only arguments that is necessary is geometry first, and geometry equals to the geometry, and a scale, a spatial resolution could be 500 meter. And now through the union, I can integrate all sections, all multiple layers into a single layer. So with margin errors, number one could be number 1. So finally, the function should return a result here, and the result, for example, is return. The result is urban vector. So, and now we need to apply this function on the Landcover map. Make a variable urban class, for example, equals to function urban layer has an input that is Landcover. Finally, the urban class showing one vector layer for the urban regions. Run the code, and yes, the urban vector is wrong here. Write it again. In the panel, in the right panel, you can see finally we have one feature collection. So to show the urban layer, use map.addLayer urban class. As you can see, all urban areas showing here. This is the primary map, and also this is the urban areas that is converted from the grid structure to the layer. And now we want to get the temperature for the urban regions in this area. So it's very simple things. So through the print, call user interface chart image.series function, multiple arguments available here, replace image collection by temperature layer with degree Celsius units. The region here should be urban class, and as we want to get the average of temperature for urban area, Earth engine.reducer.mean, and then a scale should be 500 meter, and X properties should be system time start. Run the code, and after a few seconds, you can see the temperature of urban area in this region. First, we got the temperature of the water areas, and now we will have the temperature of urban areas. As it is expected, the range of temperature in urban area is a little more than water area. As you can see that in the urban area, the temperature coming to, for example, of 40 degrees Celsius, but the maximum temperature in water area is 30 degrees Celsius. That makes sense. So I hope you liked this tutorial, and also if you had any question or any problem during the programming steps, feel free to reach me out and ask me questions, put your comments, and also it should be noted that the code is also available in the description part of my video in my YouTube page. Thank you for your attention.